Hello everyone, welcome to the first recitation of IDL. In this recitation, we will go through some key concepts in multi-layer perceptions to get you familiar with them and also show you how they are working together. First, let's start from some overview of the neural network. In the lecture, we discussed about the neural network as an awesome biological system that enables all our human activities. We talk, walk, and also make decisions because of it. If we zoom into the neural network, we know that neural network is actually lots of neurons connect together. Each neuron is a node with many inputs and one output. And information are sent from one neuron to another and create response. The biological mechanism is awesome and important for our human beings. However, how can we take advantage of those biological inspirations? In here, we have the perceptions. Each perception is a single layer neural network, and there are four parts in the perception. First, the input layer. Second, weights. Third, weighted sum. Fourth, threshold or the activation functions. So how those things come together to let perceptions do their work? First, all inputs are going to multiply with their weights. Notice here, inputs and weights are one-to-one corresponding. Then we sum all of those multiplied values together, which is the weighted sum. After that, we apply activation function to the weighted sum. For activation function, you can think it as a way to squash value. For example, you may have weighted sum from the range of negative 10,000 to 10,000. And if you apply sigmoid, it will squash it to 0 to 1. More importantly, activation function add non-linearity into our MLP network. If we only use linear function here, the whole network will become a linear regression. In here, I use a very simple single layer perception to show how it is used to do the linear binary classify. As you see, by using this perception, we are able to classify inputs into two classes. The weights shows the strength of the particular nodes, and the activation functions are used to map the input between the required values. If we know how to use perception to do the binary classification, the second question come to us is how can we distinguish between more classes? The very intuitional approach is to have more perceptions and stack them together. For example, here, we use these three-layer perceptions to classify three classes. In here, we have one input layer, three hidden layer, and one output layer. To notice that in MLP network, only weights and bias are learnable variables. Others are just hyperparameters. Next, we will have a detailed look of how those network is learned.
Hi, this is Fu. Let's move on to talk about how the neural network is learned. So first we want to know what do we need to learn. Given the structure, given the neural network structure, the only thing we can learn is the parameters or say the weights and bias. Basically the weights and bias give the output of each layer. And here we represented by the connections between the two neurons. And for say we are trying to model an actual function, but we don't know the formula of it. However, we are given a bunch of sample data points on this function. So we can use the neural network to estimate the functions with the given samples. But we still cannot directly get to the formula. Our goal is only to estimate the function. So here we introduce the measurement of error to tell how good our current estimation is. It basically tells us how much off is the network output with respect to the desired output. Cool, let's take a look at how to calculate this loss function. So here we have the sample value x, which is the input of the multi-layer perceptron, and w, which is the set of the weights for the estimated function. And given the structure of MLP, we can directly get the output of the network. So here what we want to know is the is the difference, the off between the network output and the desired output. So we introduced the divergence function, which basically tell us how far off the two values are. It can be a simple subtraction, mean squared error, or even KL divergence, or anything. And after we got this divergence, we want to take a mean over the divergence to keep the loss in a reasonable range. At the same time, it can still tell us the off between the network outputs and the desired output. So after we get the loss, let's recap our goal. What we want to do is to model our modulator perceptron to tune up to learn the ways that can minimize the loss. So here we introduce gradient descent, and we'll cover this topic in the following lectures. As you can see, it basically moves the weights into the direction that can minimize the loss. So let's take a quick recap to make sure the definitions are clear. So given the MLP and the input, we want to use the forward path to calculate the output. And we compare the estimated output with the desired output to get the loss. And our goal is to find the optimized ways to minimize the loss. So here we calculate the derivative of the loss and use the backward propagation to pass the derivative back to each neuron to calculate the derivative of each weight. And after we get those derivatives, we fit it into the gradient descent and use the gradient descent to update each parameters. Let's take a look on a small example. Basically, it is the progress of the forward pass on a single perceptron. For say, well, we have a simple structure and we have three inputs, X, Y, Z. We can vectorize it to a capital X, which is the vector of small x, y, z. And we also have three ways to map them and take the summation over the input. We can also write the weights internal vector, W1, 1, W2, 1, W3, 1. And this is the set of the weights. And if you want to consider the bias, we can also write it as a neuron. Well, if you want to count it as a part of the weight and add it together, we can let the input of 1 and make the weights equals to B. In the forward pass, a single perceptron will have two operations. The first operation is the affine operation, which is basically multiply the weights on the input and maybe add up the bias to map it to another space. So here we calculate the summation of the multiplication between weights and inputs as Z equals to, let's make it a multiplication of the two vectors, which is the W transpose multiply X. And if you want to count on the bias, we just add the bias term after it. And yeah, the second operation is the activation part. You can use threshold, ReLU, or any activation functions you want, but for here, we want to use sigmoid. And after the activation part, we can get the output y equals to, y hat. This is the estimated output. Y hat equals to sigmoid Z, which is the sigmoid W transpose X plus the bias term. And we can take this one as the output of the single perceptron. And yeah, after we got the output, we want to calculate the loss function. So for say, given a pair of sample data points, given the pair of input and desired output, we can get the loss given the parameter, given the weights and the inputs. First, let's take the L2 distance as an example. It should be 1/2 times estimated output, subtract desired output, and square. Yep. So this is basically the forward pass of a single perceptron. Okay, let's move on to the backward pass for a single perceptron. So in the backward pass, what we want to get is the derivative of the loss with respect to the weight itself. But we have to apply the chain rule to get this one. So we first calculate the derivative of the loss with respect to the estimated output. And then we want to get the derivative of the estimated output with respect to the weight. And we can keep expanding the second part and make it to the derivative of the estimated output with respect to the z, which is the parts before the actuation. You can also view this one as the output of the affine operation, and times the derivative of d with respect to the weight. So here we use partial derivatives because we have multiple input, while we only focus on the partial derivatives of the loss with respect to the weight, the W itself. And let's take a look at different parts one by one. So for the first part, given the formula of the loss function, we can simply get it as the estimated output minus the desired output. And for the second part, it is basically the derivative of the sigmoid itself, which is the sigmoid z times 1 minus sigmoid z. And this one is trivial to calculate. So you can take a look at the formula of the sigmoid, which is the 1/1 plus e negative b. And from this one, you can simply get the formula of the derivative of sigmoid. And the third part is the the third part is x. Okay, and for now, we have already gotten the derivative of the loss with respect to the weight W itself. And yeah, this is basically the forward pass and backward pass for one single perceptron. And it is basically the same for the multi-layer perceptron. In the forward pass, we first calculate the output of the first layer to the second layer, third layer, and eventually the output of the multi-layer perceptron. And then we compare the estimated output with the desired output and get the loss. And after that, we calculate the derivative over the loss function and apply the chain rule to gradually go back and eventually get the derivative of loss with respect to the weight. So we first calculate the derivative of the loss with respect to the output, and then we gradually go back to the last layer and to the second last layer, and eventually all gradients of weights with respect to arrow are calculated.
After we know how to calculate gradients, we then can update weights by choosing learning rate and use this equation to update weights. However, choosing learning rate is an art. Sometimes if you choose a learning rate that is too large, you may cause the model to overshoot. which means that the model will have worse performance as a model training. The ideal situation is that we start from some large learning rate to let the model converge faster, and then get smaller learning rate to reach the optimal point. We all know that we are going to use the gradient descendant to update weights. However, if we compute the gradient descendant towards the whole dataset, it will be really slow and expensive. Another approach is to use SGD, which means that we are going to calculate and update weights by each batch. This will cause another issue, which is the fluctuation. For example, if we have the converge point and start point in this direction, then the fluctuation of the SGT situation will be something like this. So there are also multiple ways we can optimize this. The first is the momentum. We can use momentum to memorize the pre's moving direction, and then we can avoid all of those dramatic change in those directions. So the result could be something like this. Another way is to use ADAM grad, which is the short of the adaptive gradient. This approach adjusts the gradient by including a regularizer here. And the regularizer has the sum of accumulate square of the gradient in the denominator. Therefore, at the early stage, this regularizer will be large, so it amplifies the gradient. And at the final stage, it will become really small, and it adds penalty towards the gradient. ADAM is another approach that is similar to ADAGRAD. We showed it in the second page. So the ADAM is, so the only difference is that it computes not only the first derivative, but also the second derivative, and use them together to adjust the gradient. And then we also want to introduce some visualization approach that you can visualize those laws. So you can see here all of those contours is actually the loss, and then you can see this is like a direction of the gradient descendant. And then we also recommend you to test and play with this TF playground. It can let you to understand how those models get converged, and then in what situation it cannot get converged. Thank you.